This presentation was created for the System ID and Controls Lab in ME 4056 by Chris Link, Samuel Ranck, Cameron Whiteman, and Jacob Peloquin. In this presentation, we will discuss our purpose for conducting the experiment, the theory guiding our setup and analysis, and the methods used to conduct the experiment. We will then present our analysis of the effects of voltage and mass on the motor gain and motor time constant, and of the dead zone and saturation limits of the system.
The purpose of this lab was to characterize the modeling parameters, such as motor gain constant and motor time constant, for a DC motor provided by Quanser Incorporated, as well as look at the range of input voltages which elicit a linear response from the system. This leads us to three main objectives for the experiment. The first of those being to experimentally determine the motor gain constant. Then from that, we can find the motor time constant. And finally, by looking at the response across a range of input voltages, we can determine the dead zone and the saturation zones. Finally, moving forward, we'll use these experimentally determined parameters to design and tune a motor controller to meet the specifications of our customer.
The system is a DC motor and can be modeled using the Kirchhoff voltage law. Using the Laplace transform in system dynamics, a transfer function can be determined between the voltage and the angular velocity. The system is a second-order system, but by neglecting friction and armature induction, the system can be simplified to a first-order system. The transfer function coefficients are defined as Km and Tm for motor gain and motor time constant. By applying a step input voltage and analyzing the resulting angular velocity, values for Tm and Km can be determined.
Experimental setup were comprised of first an electronic mass scale used to measure the mass of the three flywheels. Next was a DC motor provided by Quanser Inc., as well as the electronics accompanying it. On this motor setup, there's an optical encoder that reads the angular position of the flywheel as the motor drives it around. The characteristics for each trial are input into the computer and executed by the DAC MyRio. Additionally, the MyRio reads the output of the optical encoder and transmits that back to the computer. The procedure for this lab was to first use the electronic mass scale to measure the mass of each flywheel. We're then able to run multiple trials across a range of voltages and masses and record the angular velocity outputs of the DC motor. Using these trials, we could find the steady-state angular velocities and perform a linear regression to calculate the motor gain constant. Additionally, with these motor response trials, we were able to determine the motor time constant for each trial and average that across the board. Finally, by inputting a wide range of voltage inputs and looking at the response of the setup, we could determine the motor's linear working range.
Using the procedures that were mentioned in the methods section, we were able to collect data for the angular velocity versus time of each of the 30 combinations of voltage and mass. So we had 5 different masses and 6 different voltages. We were able to then plot each of these trials. So on the right here, I have 2 examples of the 0 gram mass with each of the different voltages, and then the 127 gram mass with each of the 6 voltages. And then using this data, we were able to determine the steady state angular velocity of each trial, so the portion where it flattens out here. These steady state angular velocity values were then plotted against the input voltage for each trial, and we get a linear relationship here, and the slope of this line becomes the motor gain Km. So we calculated the Km for each mass by using the steady state angular velocity and voltages. Using the inverse Laplace transform, we were able to determine this relationship such that the angular velocity is directly proportional to the input voltage times the motor gain. We then calculated the motor time constant for each of the 30 combinations of mass and voltage. The time at omega star, or also can be thought of as 0.632 times the steady state angular velocity, was found. At this time, the time constant is equal to time. So we determined that the time constant was this t value. We had already determined omega steady state previously, so we just used that value and multiplied it by 0.632 to find omega star. We then determined the average Tm value for constant voltage in all masses and constant mass in all voltages. Using the data gathered previously, we determined the effective mass and the effective voltage on the motor gain and the motor time constant. We plotted the motor gain against the different masses, and you can see that there is quite a linear relationship, and that the effective mass is insignificant on the motor gain. The voltage was used to calculate the motor gain. As we compared the omega steady state values to the input voltage, we found that slope which determined our motor gain. To determine the effect of mass on the motor time constant, we plotted the motor time constant versus mass for all of our trials. As you can see, each of these relationships increases linearly. So we determined that as mass increases, the motor time constant for the system will increase linearly as well. To determine the effective voltage on the motor time constant, we plotted the motor time constant versus input voltage for each of the 30 trials. As you can see, for a given mass, the motor time constant decreases slightly as you increase voltage. However, in theory, this motor time constant would remain relatively consistent as you increase the voltage. This may be due to the modeling assumptions made and the fact that this is in reality a second order system, and we simplified it to a first order system.
Regarding dead zones, the motor has a nonlinear response during the input of low voltages. This occurs from roughly negative 0.4 to positive 0.4 volts of input voltage. At these low levels of voltage, the motor does not have enough power to spin properly, thus waveforms such as the example shown here are produced. The output waveforms have a lot of noise and near zero amplitude. Past this point, the steady state angle of the output waveform reaches the linear band where the steady state angles increase or decrease linearly with the input voltage. This continues until the system reaches a saturation point at negative 7 or positive 7 volts with an amplitude of 64 revolutions per second. In order to confirm that the saturation point was in fact at 64 revolutions per second, a second test was performed with an input voltage of 9 volts. The saturation point with an input voltage of 9 volts yielded the same results as the input voltage of 7 volts, thus confirming the previous specified saturation point.
Next, a further test was conducted using an input voltage of 15 volts. This test was to confirm the upper bounds of the system saturation level by confirming that there be no increase at a higher input voltage in the steady state wave angle. The result depicted here shows that the 15 volt saturation point was consistent with the previous 7 and 9 volt points. This represents the upper bound of the system. Above or below these values, the system becomes saturated, where adding or subtracting voltage causes a corresponding increase or decrease in the output waveform steady state angle. In other words, the slope of the graph voltage versus steady state angle becomes 0, as seen here. This occurs because the motor is no longer able to translate higher input voltage into physical motion. It has achieved the maximum rotation possible for the given system, which has produced the saturation that we see here in the graph.